Okay, so chapter 5 is about motors, actuators, and engines, and about matching them with the load. We understand by motors primarily electric motors, and assumption is that they provide rotational motion. Engines in automobiles, although sometimes also called motors, power the wheels and auxiliary systems, including, say, a hydraulic pump in a tractor or a concrete mixer. And they always employ in engines on automobiles. They always employs a gear reducer. Invariably, these are multi-step gear reducers. Actuators provide linear motion, and they could be of the piston rods, the actuator, the moving part, or solenoid core, and they rely on fluid power supplied from a pump or accumulator, or electric power from a battery or from other power supply. Their type is very diverse. So I have here a list of them. Continuous rotary input motors, like well, this should be output. Okay, so just change continuous rotary output motors, like electric motors running in direct current or alternating current. Air motors, think impact wrenches used in auto garages and or dentists, drills. There are some of them are powered by an air motor. We have hydraulic motors, and I mentioned earlier concrete mixers, so or vehicles, slow-moving vehicles with hydrostatic transmissions. There are internal combustion engines. There are gas turbines. There are external combustion engines like the Stirling engine, and maybe more. Actuators, linear actuators, could be air or hydraulic cylinders. Both could be single or double acting. We can have membrane actuators, like in some braking systems for trains or 18-wheelers, and then there are solenoids that also have the output performs linear motion. Okay, so electric motors, what they do, they convert the electric energy into mechanical energy of a rotating shaft, and there's interactions between the electromagnetic interaction between the stator field and armature current, or stator field and armature field, and you'll see parts that make for electric motors are rotor, stator, armature windings, commutator. If it's used as a servo motor, there is a shaft encoder, controller. Sometimes there's a gear head built in with the electric motor. One of the very common electric motors are the permanent direct current PMDC motors, and you see them everywhere. They are used in battery powered hand drills, in toys, various actuations on a automobile, on a car. So the motors that drive the fans, the AC fan or the main radiator fan, the motor or motors that drive the windshield wipers, even power locks are actuated with motors rather than solenoids. So the stator is a permanent, and the rotor has armature, windings, and commutator. And so here's are the main parts of a permanent DC motor. And so you have the permanent magnets, you have the commutator, and pair of them are connected to one loop, or rather winding, independent winding of the rotor. And then there are the bearings supported by the plates. We have the brushes, oftentimes graphite. For small size motors, they could be just blades that maintain contact with the commutator. For force cooling, you can see a fan and cover to the fan, if it is the case. The way a DC motor works is through the interaction between the constant magnetic field produced by the permagnet and the DC current that runs through each of these armature windings. And there's more than just one loop. There are multiple loops, but here is shown just one of a single one. And interaction between the current vector and the field vector, the right-hand rule, it's a cross product you remember from other classes, creates this this magnetic force that tends to rotate the coil, and together with it the rotor. Now, a motor of this design will not be able to self-start, but it will run. So if you fabricate, it's missing the rotor, but you can introduce a shaft supported on two bearings. The commutator has only two blades, and then you have the brushes seen here. So you can have this run as a motor, pretty inefficient and not self-starting. In order to start it, you need to give it a kick, and once it reaches the desired speed, it will continue to rotate. We usually operate with as mechanical engineers who are more concerned with their capabilities in size and flanging possibilities to use them in our designs. And of course we care whether it's what voltage does it run. So common values are 7.2, 9, 12 volts, could be 24 volts, 48. The way we deal with them again and match them with load, one of the objects of this chapter is by studying their curves. So here's a schematic of the motor. This is the permagnet. Should probably have a second mirror image. Maybe I cropped this figure. The DC voltage supply, power supply, and then we have the torque, speed being RPM of the rotor shaft, and the torque varies with speed linearly. Same varies linearly the current and torque, and implicitly current and speed, they vary linearly, which are advantageous for control applications. Also listed here is the rated torque and the rated speed, and rated torque and rated current, which are pretty small compared with the maximum torque that the motor can produce. This is the stall torque when the speed is 0, something that those of you that have used battery power tools like hand drills to drive wood screws, for example. So at the end, in order to provide the maximum tightness to the wood screw, instinctively you sense the twist at your hand at its maximum when you squeeze and release the trigger. So by doing so, you operate the motor around this, around the stall torque, which is a maximum. Now, you cannot do it for too long. You cannot hold the rotor shaft immobile and supply power to the rotor, because you can damage the motor. That's why the rated torque and rated speed. You want to alternate the current through the windings of the armature, give them opportunity to cool, and also have the fan rotate to force cool the armature. But as this diagram shows, the maximum torque is at 0 speed, which is it's good for many application. You start full load, say in case of little ride-on toy for children, or power tools. So when you have the stall torque, you have the maximum current. So the current through the drag from the power supply is maximum at the stall torque. Okay, so I have here a photograph. They are from my own vehicle, an older vehicle that I own, and it shows the little permanent DC motor with the gear reducer. This is a worm wheel gear and one additional reduction stage, and there are two of them, as you can see, serving to orient the side mirrors. One of them. Okay. And there are other permanent DC motors called brushless, where the rotor part has a permanent, and it's the stator that runs a magnetic field that is controlled by electronics and provides continuous rotation to that magnet that is attached with the rotor. They are long lasting because the brushes, they don't wear out. Maybe you experienced, at least I did, had issues with a AC fan motor of a vehicle that I owned, and the brushes, they just wore out, and to the point where the motor was no longer rotating, the graphite brushes. So you see the brushless permanent DC motors used in cooling fans for computers and other types of electronics that requires force cooling. Here are the sample curves of an actual permanent DC motors. You should be able to get, if working on a project, you should, and if the supplier is a reputed one, you should be able to get from them these type of curves. So what we have the horizontal axis is a torque axis, and then we have multiple y-axis. So we have the first is the RPM axis. So torque versus RPM would be this curve. It says N. And then we have torque versus current. This is the second y-axis. So you can tell some like performance parameters. What would be the maximum RPM? What would be the maximum current, the stall current? Then we have the power curve. Okay, you can see power maxes around half of the at around half the RPM, maximum RPM. And then there's the efficiency. So if you record where the efficiency is maximum, as you can see, is at a fraction of the stall torque, and you can also tell the RPM. So if you want to maximize the for steady state operation, if you want to maximize the use of battery power or converting battery power into mechanical power, you should consider operating the motor at its maximum efficiency, and that should also coincide with the operating the rated speed and the rated torque for the motor. So it should be in terms of heat dissipation and sizing the fan, it should be such that the rated torque, rated RPM are around the maximum efficiency. Other type of DC motors are the shunt wound motors, and here we have a field coil that is in parallel to the rotor windings, and you can even interpose a variable resistor, and you can adjust the speed of this motor by varying the field current. So if you look at this figure, again, the magnetic field comes from a permagnet, but you can instead use a coil to produce this magnetic field. Is DC current running through the coil, so this field is steady field, but by adjusting the current through the stator coil, you can reduce the B value, and with it control the speed of the motor. The torque speed curve typically looks as shown, and then the current is neither as linear like for the permagnet DC. It could look like shown here, and as you can see, the rated torque is less than half at least at the scale of this drawing than the stall torque. So a motor like this one, it's good because you can adjust the speed easily with a variable resistor, but does not have a significant, compared to the permagnet DC, does not have a significant stall torque to help with at startup breaking the inertia. So as you can see, so it's only like 50% stall torque greater than the rated torque, and they are used only for only certain applications. Again, the possibility of varying the speed is a desirable feature, but not having a substantial stall torque over the rated torque, makes them useful mainly for fans, blowers, and similar applications. Here's a motor, a series wound DC, which you see used in at least the older designs of go-karts, and or the starter motor on every vehicle to start the engine, crank the engine. They use this type of series wound DC motor, and they have this ability of creating very high stall torques. So 80%, 800 or 8 times higher than the rated torque, and conversely, when there's no load, they can reach very high RPMs. So you need to be able to limit, never let them rotate without a load. So you have a heavy coil in series with the rotor windings, and the windings are, if you have had a chance to open up a startup motor of an engine, I opened up a motor coming from a go-kart, and the windings were thick wires, even could be even copper flat bars, insulated as winding. Okay, the current curve looks as shown here. You can match the rated torque and get the rated current. Again, information useful, and all these, by the way, should be, the diagram should be given at a specified voltage. Could be for different type of volt. So you can have a motor that is rated for, or you can power it at 12 volts. You can power it at 9 volts. Curves will look different, of course. Will be less. So if I have an electric motor of a engine starter is rated for 24 volts, you can power it at 12 volts, but you'd expect to have half, if not less than half, of the maximum torque. Okay. There is a combination between the series and the shunt, the parallel wound DC motors, which are the compound wound DCs. And here you have the current from the power supply split into a series, going through a coil in series, and then another one that is so again it's the current split, and the torque speed curve starts looking like a combination of the earlier two motors, with an increase, welcome increase of the stall torque versus the shunt wound design. And it's self-limiting, does not run away, does not get to very high speeds, and application could be it is listed here, cranes and hoists and other applications. I should have mentioned the hyperbolic torque speed curve corresponds to constant power, and this is desirable on anything that's on wheels, and as power source for vehicles. Okay, so you would see them for continuous use in go-karts, I said, and starter motors of any automobiles are of these design. AC current motors, they are of several types. There's a classification diagram here in figure 9. So you can have them single phase or polyphase. Most common are 3-phase motors, and they could be induction motors, the most common ones, and synchronous motors. So in induction motors, they have a rotor circuit that is not powered through wires from the outside, through cables from the outside, and it's just so it's current that's induced by the variable field of the stator induces current into the windings, could be squirrel cage or wire windings of the rotor, and their interaction causes the rotation of the rotor. Again, these are the most common ones, the induction. And then you have the synchronous types, and they could be paramagnet, shaded pole, hysteresis, reluctance. So examples of synchronous motors you would see on electrical clocks. Like you go to a swimming pool and there's that big clock. You can time yourself, or in some classrooms on campus. Also, microwaves, they have synchronous motors used to drive the platter. And if you've noticed, sometimes the platter rotates one way, sometimes rotates the other way. For clocks, in order to rotate the same direction, there is a one-way clutch used. And then on the single phase induction motor, they could be in order to amplify the stall torque, so you have higher torque available at startup to break up static friction and inertia. It could be capacitor start, 2-value capacitor, split phase. They're the shaded pole. We'll discuss them for a little bit. That use other means than capacitor. So the split phase, but capacitor start are the most common ones. You see them with AC unit motors. They run in single phase, at least the residential ones. And then for the wound rotor, there could be repulsion, repulsion start, repulsion induction. These are less common. The squirrel cage is the most common. So if we look at this is the asynchronous motor cutaway view, and they're highly reliable because they don't have moving contacts. At least the 3-phase ones, they don't. So the stator windings, you see them here, and then the rotor has 2 rings, and then there are bars actually cast through the lamination of the armature, and those bars get energized, so there's current running through them caused by the variable magnetic electromagnetic field of the stator. Again, it's alternating current, and they interact with the original magnetic field of the stator, and it causes rotation. Okay, and if you look at the number of contacts, so yeah, this is a 3-phase, but for single phase, you need a means to start them from rest, to break the inertia I said, to reach their operating speed, and it's where you need to supplement. You need the capacitors, and you need the maybe governor switches. Okay, so for induction, 3-phase, primary polyphase, you can have that squirrel cage or wound rotors, and then there are universal motors, separate category. These are commutator type motors. They can run both in AC and DC. On the synchronous motors, the permanagnet type, I've seen them with like the drain pumps, or some actually old drain pumps that I've seen on dishwashers. Not the main pump that churns, that circulates water for with detergent to wash the dishes, but rather the motor to empty the dishwasher to bring fresh water for rinsing, say. They are permanagnet synchronous motors. With synchronous motors, you need to, at least a polyphase type, they have high efficiency. They have other uses. My knowledge of electromagnetic and electric machines is a bit up to date, or I forgot things since I took the respective classes long ago. But for the polyphase, you need to bring them to the synchronous speed before you can use them. And being high efficiency, you see them used in large application, like large pumps for utility works, or to circulate air through tunnels, on subways, or in mines. Anyway, so there is what is called synchronous speed, and it's function of the frequency of the line, the number of poles. So frequency of the lines could be 60 or hertz or 50 hertz in Europe and Australia, elsewhere. Yeah, so things that alternator in an automobile is actually a synchronous electric machine that is used as a generator, and it has moving contacts which can wear out. One mode of failure of alternating automobiles is the wear out of the graphite brushes, out of being bearings, I would say. Anyway, so a synchronous motor, you can see the moving contacts. So you have the field coils, you have the alternating current, and essentially the coil of the rotor gets locked with the rotating magnetic field and moves with it. Okay, so there is a rotating magnetic field coming from the field coils, and these lock with them the current, the field from the windings of the rotor. Okay. In asynchronous motors, this synchronous speed, likewise, you can count number of poles and the frequency, but they don't reach. They get close when there's no load, but they don't reach the synchronous speed. There's always sometimes of a slip, and as you increase the load, the slip increases. We looked at this figure, and again, in terms of their torque speed curves, they can have various appearances. So this is a shaded pole, has a very low stall torque. They won't be able to start under load. This shows the rated speed, rated torque. In order to achieve higher stall torques, to break the inertia, to be able to start under load, think AC units. Residential AC unit compressor. The commercial ones, the larger ones, they run 3-phase. That's less not of an issue, and they use capacitor start. And you can see the dashed lines. This is a switch between the two modes. It's controlled by a centrifugal switch. Okay, if you go to the machine shop and if you flip the switch of any of the grinders, and then you flip it back off, and see there, you can hear the toggling of the governor switch. Simple sample problem. So for 4 poles, 60 hertz, the RPM, nominal RPM for a synchronous machine is 1800, with slip considered. Sometimes values like this one, maybe, let me change this because it's a very common nameplate characteristics of asynchronous motors. So it's less, 1750. Okay, so here's the picture of a shaded pole single-phase induction motor. No moving contacts, very long-lasting. You see them in bathroom fans. Of course, what their demise is due to the built-up, the dust, the dump or wet particles. They can clog the rotor, and having such a low stall torque, you can burn them. You flip the switch, and if you don't flip it back off, the coil gets energized, and not having any circulation to cool and to start up the current. It's also higher than the nominal torque or the current. You will burn the insulation to the windings and damage the motor. These are the shaded coils. So what they do, they deflect there's current induced into them, and they deflect the magnetic field and allow it for the motor to start. You can run an experiment. If you have one of these available, you can use a wire cutter to cut these off, and you'll see they don't start. But if you give it a kick, it will start rotating. The rotor is the same squirrel cage type, like for other asynchronous machines. The three-phase induction motors, there are different designs. So you see the design D has the most stall torque, usable when or useful when you start under load, like in conveyor belts. And then the other designs are design C and B, with B design having the lowest of the stall torques. Okay. NEMA stands for National Electric Manufacturers Association. Okay. You'll see problems from me where the type of design is design D, because the curve can be easily approximated with a parabola. And then we have the universal motors. I mentioned they are essentially they can run in both AC and DC, and you see them on applications like vacuum cleaners or corded drills. They produce relatively large torques for their size, but they are noisy. They have commutators that can produce sparks. You cannot use this type of motors in explosive environments, like you can have explosion in coal mines due to the presence of methane, which seeps out of coal layers. You can have explosive environment when you have dust. I know of a story where there was an explosion on a factory that were they were, I think, flour, wheat flour, was it paprika, pepper powder in suspension gear, and exploded. FYI, there are large diesel engines that use coal powder as a fuel to burn the coal powder inside of the cylinders. Okay, so these are universal motors, very common. Like I said, if you take apart any vacuum cleaner or a corded drill or any power tool, corded power tool, will find this type of electric motor, or a kitchen mixer. For control applications, you see servo motors. What type of control applications? For example, numerically controlled milling machines. If you go to the machine shop, I'm not talking about the machining center, I'm talking about the Boxford mill. There are servo motors with gears that accompany each of the 3 degrees of freedom. The table opposite to the x-axis crank, there is a motor. There's one in series with the Y crank, and there's also for the coil to move it up and down. As you can see, you can find this is a planetary type gear, 2-stage apparently, but they also have on the shaft they have an encoder which allows the electronics that controls the motor to tell what the position of the shaft is. They could be absolute encoders or relative encoders. This appears to be a relative encoder. You see only equally spaced slots that allow the wheel, or rather light, to pass through, and it'll count pulses of current recorded by a photodiode, and counting those, you know how many turns, or the fractions of a turn the rotor shaft did. So with these, you can program function, smooth start, and steady motion, and then coast down. Also usable or used in other than America controlled machine tools. You see them in large robots, or in controlling flight surfaces on unmanned aircrafts or missiles. So again, there's the computer as electronic that modulates the voltage through the windings to provide the desired motion to the rotor shaft. Stepper motors also used in control applications, but more of the light duty types, such as small manipulators, small robots, 3D printers, pen plotters, or copy machines and scanners. So one example is where you have a DC motor, and there are other designs. So brushless permanent magnet, variable redundance, or hybrid types. But for the DC type that's explained here, so the rotor is a magnet, and then you have windings that can be energized, so number of poles, and their number gives the resolution of the stepper. Here's one. You can see it's not just 2 cables, or maybe 3 if you want to reverse. So more than 2 cables, depending on the number of poles, and they are marked. Their resolution is marked in degrees per step. It's marked on the body of the motor. Of course, with the right reduction, you can rotate the output shaft small increments. Say the resolution of the motor, the stepper motor itself, is 7.5 degrees, but with a reduction of say 10 to 1, you can drop to 0.7, that is 3/4 of a degree resolution. Anyway, the circuitry used to control the stepper, and the way they can operate, again, the permanent type. So you have north and south, and you have the poles, and in a hold position, south was aligned with the north, and north adjacent poles. Here are just 4 poles, and north was the south and south. In order to rotate to the right the motor, you change polarity of the poles. So you hold this to north, but you change this to south, and you change south to north here. So the magnet follows and aligns itself south with the 2 north poles, of which one is new, and likewise north aligns itself with the new south pole and the old south pole. So this way you got what, a quarter of a rotation, and then you can continue. You can rotate 90 more degrees. So the resolution of a motor like this with only 4 poles is 90 degrees. If you increase the number of poles, then you can rotate a fraction or less than 90 degrees. Could be, if I double the poles, I can rotate 45 degrees and so forth. Okay, so stepper motors, again, widely used. You see them in there's some dashboard analog indicators that actually use steppers to drive the hands of the speedometer, of the tachometer on the dashboard. Maybe you've seen vehicles where you first crank the engine to give a feeling of power available. They go all the way to the end scale for a couple of seconds. Again, those use small size stepper motors to do that. Okay, solenoids. Solenoids are very common with relays, electromagnetic relays, but also used in electromagnetic latches, and the starter motor of an automobile includes a solenoid that does two functions: acts as a relay and also engages the pinion with the ring gear on the flywheel edge. So when you turn the key in an ignition switch, you're energizing this coil, and it the core, it's attracted inside. It closes a high current circuit to power the starter motor. It is a Series 1 DC, and also moves. It's pivoting here, and this yoke move. It has a one-way clutch, moves its pinion in contact with the ring gear on the flywheel. By doing so, you run very or low current through the ignition switch, and you have a short, thick wire connection going from the battery to the starter. The circuit closes through the chassis. The minus is the ground, the chassis of the vehicle. Okay. So here are two type of design: the plunger type and non-plunger type. So you energize the coil. There is a spring that keeps the armature, removable armature, in a non-energized position, and you work against the springs to move the coil inside. Here, when you energize it, there's the magnetic field and forces this to close the magnetic field of the this U-type iron core, and has a higher holding force ability, a solenoid like this one of this design. Okay. I do have, let's see, if I go to where my notes are, so I have, so was, no, sorry, notes, motors and drives, and I might go back to these, but I want to show you a tiny application. I did the animated GIF for this, so it was sort of animated ad on a box of a corded floor swiper from Shark, and you can see the solenoid. In addition, there it has a little speaker, the batteries, the electronics that produce the voice, the sound, microprocessor, microcontroller, and also has the solenoid, which is energized in both directions to provide. There's no spring here, or is it? I don't recall. It might be one hidden. Anyway, so an example of solenoid application, FYI. The other type of linear actuators are membrane actuators, and you see them in air or steam control valves You see them in the brake system, servo system of automobiles. So the suction, the negative pressure from the intake is delivered to the to the one side of the membrane of the brake booster, and it helps with the brake force, the driver. There are pneumatic brakes that use membrane actuators. There you actually have, if you go back to the first class recording, so the compressed air works against a spring and disengages the brake. If you lose air pressure, the brakes are engaged by the action of the spring. So we can analyze. These are the two designs. So the supplied air could either open the valve, and if you lose the air, the valve is closed, or vice versa, depending on which side of the membrane the air is applied. Climatization systems of automobiles also use vacuum to move some valves and direct air towards the or behind the wind shield, or towards the passenger and driver, or towards the feet. Okay, air and hydraulic linear actuators, also know hydraulic cylinders, pneumatic cylinders. So you have linear displacement of the piston rod. Power comes from pressurized air or steam or hydraulic fluid. Steam, could be used. Think of catapult launchers on aircraft carriers, or your steam presses still use the large ones to drive forges, used as forge hammers. So their response is, if you have constant force and you work against a steady resistance, they accelerate linearly. And you can have impact at the end of the travel. So for that reason, you can have there are designs where towards the end of the travel, the inlet is progressively reduced to reduce that impact. They could be single action pressures applied on just one side, and it's always going to be the side where it is not the road, or could be double action. Here you rely on gravity, say, or on a compressed spring to bring the actuator back into the retracted position, or you deliver pressure on either one or the other side of the cylinder. There are actuators that could be, the rod could be through rod. You see them in actuating the steering of the hydrostatic steering of some vehicles, or boats. Okay, electromechanical linear actuators, you have a motor with a reduction and you have a power screw. And so here's where it's missing the rod, or it looks like a tubing with a nut to it, and with the ending with the clevis, but it pivots relative to these two bearings, and here's where the output link is connected. Usually you see them as inversions of that slider crank of the type rotation, prismatic, rotation. We want to go back to earlier chapter 2, chapter 3. Okay, air and hydraulic motors. So you have a flow of pressurized air or hydraulic fluid oil, and it rotates continuously. A rotor, it could be of this design, a vane type, could be of other type like the piston type, and you can even adjust the speed, the speed to some of these is adjustable. Next time you see a concrete mixer on the road, watch for, it looks like an elbow contraption at the end towards the driver's cabin of the mixer, opposite from where it's emptied. And design like these, you can see them with pumps as well, so they could be both, could be operated as pumps as well as motors actually. And other designs of hydraulic motors will be of the gear type. So you power one of these gears, they mesh, and so the body of fluid, of hydraulic fluid, is captured and delivered towards the outlet. And then you have the G rotors. These are planetary type gears with internal meshing, and you see them as oil pumps on some engines. Okay, so when it comes to selecting the hydraulic or air fluid pressure, selecting a compressor, having this type of curves available is very useful. So this is a schematic of the air motor. See the flanging, this is the output shaft, and with it, you can find from the manufacturer this type of curve. So whether the available air is compressed of 70 psi-G or 90 psi-G, you will have the available torque, varies parabolically, like here with a maximum as shown, and then also air consumption, useful information, because based on that you can judge whether the available compressor is sufficient to power the motor or not. Okay, and so yeah, this type of curve is very useful. This is how we usually do or make decisions about selecting and using them. Okay, so I'll stop here, and there will be a separate recording on engines and some applications.